Okay, in this video I want to talk about Euler's constant. And Euler's constant, what is it? Well, the idea is if we let t sub n equal 1 plus a half plus a third plus dot 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 plus 1 over n minus the natural logarithm of n, if we look at the limit as n goes to infinity of t sub n, this sequence of numbers, it approaches a number, and we use the little lowercase symbol gamma is what we're going to use. But the idea is that sequence t sub n approaches a finite number, and that's known as Euler's constant. Now, one thing that's interesting to me right off the bat is if you leave off the minus natural logarithm of n, you're looking at the harmonic series. And we've seen that 1 plus a half plus a third plus dot 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 plus 1 over n, as you keep including more and more terms, that harmonic series diverges, okay? So we're subtracting just a little bit the natural logarithm of n, and that we're going to show that that does converge. And it's going to take a little bit of work for sure, but nothing too bad. The basic strategy, what we're going to do is we're going to show that this sequence t sub n is bounded. So that means there's, if you start looking at all the values t sub n, there's a number above that it never gets above a certain number, and it never goes below a certain number. So that's the idea of it being bounded. We're going to show that t sub n is bounded and that t sub n is monotonic. Monotonic. And we're actually going to show that it's monotonic decreasing. So if a sequence is either increasing or decreasing, we say it's monotonic. So we're going to show it's monotonic by showing that it's decreasing. And then there's a theorem that says if you have a bounded monotonic sequence, that it converges. Okay, so we're going to show that we have a bounded monotonic sequence, and that we'll use the theorem that therefore it converges. So, okay, here we go. Let's get down to the nitty-gritty. All right, so we're going to use some geometric arguments here. So the first thing I'm going to do is I'm going to show, I want to show that t sub n is always greater than 0. That's the first thing I'm going to do. I'm going to show that it's bounded below, whoops, sorry about that. I'm going to show that it's bounded below by 0. And what we're going to do is we're going to use just a little geometric argument here. So this is going to be the curve. So this is going to be the curve 1 over x. And I'm just going to make, again, a geometric argument. So here's going to be, there's 1, 2, 3, etc., dot, dot, dot. We'll make this generically n, and then we'll have n plus 1 out here. So I'm going to make some rectangles here, and I'm going to make my rectangles extend to the right. So let's see, let's make one more. Okay, so I've got some shaded rectangles here, and notice that the shaded rectangles I should say the area of the shaded rectangles. Well, what does the area of the shaded rectangles equal? Well, let's see. The first one has a height of 1 and a width of 1, so that's going to equal 1. Notice the next one, since over here at x equals 2, since it's on the curve 1 over x, this is going to have a height of 1/2. Again, it has a width of 1. So hey, that rectangle has an area of 1/2. The next one is going to have an area of 1/3, etc., etc. The very last rectangle I have here, again, since it's sitting on the curve 1 over x, it's going to have a height of 1 over n. So the area of the shaded rectangles, hey, that's given us that the basically looks like, right, the harmonic series. So, all right, no big deal there. So okay, so let's make another observation here. If I integrate from 1 up to n plus 1, of 1 over x dx. So now I'm finding the area underneath the curve. Okay, so I'm just going to compare again, clearly the area of the rectangles is going to be larger than the area underneath the curve. Well, if we find the antiderivative of 1 over x, that gives us the natural logarithm of x. Okay, normally it's an absolute value, but here we're putting in positive values, so it doesn't matter. Okay, so in this case, we're going to have the natural logarithm of n plus 1 minus the natural logarithm of 1. Well, the natural logarithm of 1 is 0, so the area underneath the curve is going to be equal to the natural logarithm of n plus 1. Okay, so again, what we just said, right, the area underneath the curve, which is the natural logarithm of n plus 1, that's going to be definitely less than the area of those shaded rectangles. So the natural logarithm of n plus 1, that's going to be smaller than 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over n. Okay, so again, the area underneath the curve is less than the area of those shaded rectangles. But also another observation, well, the natural logarithm of n is going to be less than the natural logarithm of n plus 1 because the natural logarithm is an increasing function, right? The natural logarithm of 10 is less than the natural logarithm of 11 or the natural logarithm of 12 or 100 or 1,000,000. So definitely the natural logarithm of n is going to be smaller than the natural logarithm of n plus 1. So okay, so I'm even going to put that there. So the natural logarithm of n is less than all this stuff. Well, that means if I subtract, since this quantity is bigger than this quantity, well, that means that 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over n, if I subtract away the natural logarithm of n, that's going to be greater than 0. Right? Because again, this quantity is bigger than this quantity. So if I subtract, hey, it's bigger than 0. So ta-da, boom, we've got that it's bounded below. Okay, so that's the first thing that we wanted to do. Showing that it's bounded above, we'll talk about that in a second. So the next thing I want to show, I'm going to show that this sequence, t sub n, is decreasing. Okay, so that's my next goal. I'm going to show that it's decreasing. And to show it's decreasing, that means that I would want to show, okay, what do I want to show? I want to show that t sub n minus t sub n plus 1, well, I want to show that that's greater than 0, right? Because I look at some term, and then I look at, I get some value for t sub n, I get some value for t sub n plus 1. If t sub n is larger than t sub n plus 1, well, when I subtract them, I'm going to get something greater than 0. And if t sub n is larger than t sub n plus 1, hey, that means it's decreasing. Okay, so that's my next goal, is I want to show that this happens, and that's, again, going to imply that our sequence is decreasing. Okay, we're having fun. I'm having fun. I think this is interesting. How are we going to do this, Patrick? Well, we're going to make a couple observations here, and again, we're going to just look at, make another little geometric argument. So the first thing I'm going to do is I'm actually going to come up with a formula for t sub n minus t sub n plus 1. Okay, so t sub n, we said that's equal to 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over n minus the natural logarithm of n. Well, t sub n plus 1, that's going to be 1 plus 1/2 plus 1/3 plus dot dot dot. We would have 1 over n. Well, this one goes out to n plus 1, though, so we'll have 1 over n plus 1 over n plus 1 minus the natural logarithm of n plus 1. Okay, so that's our t sub n and our t sub n plus 1. I don't think I have yet. Hopefully I don't misspeak too much through this. Lots of little subscripts and n's. So I'm just going to subtract. Okay, so if we subtract, what's going to happen? Well, 1 minus 1 cancels, the halves cancel, the thirds cancel, etc. The 1 over n and the 1 over n, those are going to cancel. Well, I've got this negative natural logarithm of n. That's still going to be remaining. When I subtract, I'm going to have this. I'm going to end up with a negative 1 over n plus 1. And then when I subtract, I'm going to end up with a positive natural logarithm of n plus 1. So I'm just going to rewrite this as the natural logarithm of n plus 1 minus the natural logarithm of n minus 1 over n plus 1. So again, this is basically what you would get, well not basically, this is what you would get if you take t sub n and subtract away t sub n plus 1. You would get that number, okay, after you plug it in and do the arithmetic. Okay, so why on earth do we care about this? Because we're going to actually make this appear in our, when we do our little geometric argument. So, all right, so let me get another piece of paper. So we'll come back to this in just a second. All right, so again, let's go back to our curve. So here's 1 over x. There's 1 over x, and I'm going to look at this between the values of n and n plus 1. Okay, so the first thing to notice is if we integrate from n to n plus 1 of 1 over x dx, we can make a couple arguments here. So one thing we can say for sure, if I look, so again, this is going to be the area underneath the curve. If I make my little, box at this height, so the area of the box here, well, what is the area of that box? The area of that box is going to be 1 divided by n plus 1, because again, I'm putting it into the function 1 over x. Well, the area underneath the curve 1 over x dx, that's going to be all this stuff. Well, certainly this is larger than 1 over n plus 1. Again, just making that geometric argument. But let's actually compute this. So just like before, the antiderivative of 1 over x, that's the natural logarithm of the absolute value of x. Again, we're assuming that these are, positive values. So again, I'm just going to drop the absolute value. So we'll have the natural logarithm of x from n up to n plus 1. Well, if we substitute that, we'll have the natural logarithm of n plus 1 minus the natural logarithm of n. Okay, so maybe that's starting to look like what we had just a second ago. And again, we're saying that this quantity is going to be larger than 1 over n plus 1. Well, same argument that we used kind of, previously. Since this quantity is greater than this quantity, I can just subtract from both sides. That means that the natural logarithm of n plus 1 minus the natural logarithm of n minus 1 over n plus 1, that's going to be greater than 0. Okay, that's greater than 0. But oh yes, this now ties back into what we had a second ago. Okay, because we said that t sub n minus t sub n plus 1, that's equal to the natural logarithm of n plus 1 minus the natural logarithm of n minus 1 over n plus 1. We've now shown that this quantity is greater than 0. And what we said at the very beginning was, we said if we can justify that that's true, that shows that our sequence is in fact decreasing. Okay. Getting close. Okay, so we've got that it's bounded below. We got that it's decreasing. It's clearly bounded above. Notice that t sub 1, if we compute t sub 1, okay, so this is now a different little thing. T sub 1, that's just, if we go back to our, our formula, t sub 1 would say basically you just go up to 1, and you subtract away the natural logarithm of 1, which is 0. So t sub 1 is equal to 1. Since our sequence t sub n is decreasing, we know that this is the largest value that you could ever get out of our sequence. So we've got that it's bounded below, we've got that it's bounded above, we've shown that it's monotonic. So QED, the proof is complete, right? We've shown everything that we needed to show. We've got that it's bounded above and below. We've shown that it's bounded. Check. We've shown that it's monotonic. Monotonic. Check. And by the bounded monotonic theorem, convergence theorem, it says, since this happens, it says that our sequence t sub n does in fact converge. What does it converge to? That's a different question. Whoops, so I am doing two different things. So t sub n does in fact converge. Now, we haven't shown what value it converges to, but that's okay. We've shown it's convergent, and that's what I wanted to do in this video. Oh, by the way, before I click off here, Euler's, this Euler constant, sometimes people use E for Euler's constant, and I've always heard this is Euler's number. Okay, E is Euler's number. The Euler constant is the number that we're discussing in this video, and it has tons of applications, and I think, I remember reading in Laplace transforms and harmonics and all kinds of things. Google it if you're interested, for sure. Check it out. It's definitely, not one of these just contrived little numbers, just, hey, look at this, it converges. It definitely has practical applications. So check it out. And all right, I hope this video was interesting to you. And if hopefully, if you're studying Euler's constant, gave you a little insight on showing how to actually show that this sequence does in fact converge.